On November 16, 2021, an experimental plane called Spirit of Innovation, designed by Rolls-Royce, reached an average speed of 556 km per hour over a span of 3 km, and in subsequent tests reached a maximum speed of 623 km per hour. By aviation standards, these speeds are not particularly notable. However, what makes it a major breakthrough is the way it was achieved. The Spirit of Innovation is the fastest electric motorplane in the world, and we are going to see it in this new video from Aviation World. This project is funded by the UK Aerospace Technology Institute and represents a major breakthrough in the research of electric propulsion in aviation. It surpassed the previous record set by the Siemens and Aircraft Extra 300 LE stunt plane in 2017 by more than 213 km per hour, and also climbed more than 60 seconds faster around some 3,000 meters of altitude. This increase in speed over such a short period of time is unprecedented in the history of aviation record attempts. In other words, the aerospace industry is evolving with this system by leaps and bounds. The Spirit of Innovation is part of a program called ASEAL, which in English would be something like a program for acceleration towards electrification in flight. It's a consortium led by Rolls-Royce and partially funded by the UK government to bring together cutting-edge technology for electric production in aircraft, and also companies like Electroflight, a startup that specializes in energy storage, and the British manufacturer of electric motors and controllers, YASA Limited, who were the main contributing partners in the project. The Spirit of Innovation is designed around an existing fuselage that was already known for breaking records, the Sharp Nemesis NXT, which is a two-seater carbon fiber airplane with a single engine and low wing specifically designed for air racing. This aircraft was previously powered by a 6-cylinder Lycoming 540 NXT Thunderbolt engine that produced around 400 horsepower. On July 30th, 2008, the world record was set by surpassing a distance of 1.86 miles at 1.86 miles per hour, and the following year it reached 653 kilometers per hour, around 406 miles per hour, becoming the first aircraft of this class to exceed an average race speed of 400 miles per hour. In May of 2018, two Nemesis fuselages were acquired and delivered to the startup Electroflight. One was designated for flight testing and the other for ground testing. The Lycoming engine was replaced by 3 electric motors and the fuel tank by 3 battery packs. Combined, the motors from the battery packs and the control equipment weighed about the same as the previous power plant. However, this entirely electric system was now capable of producing around 530 horsepower continuously and nearly 1,000 horsepower for short periods of time. Remember that we had said the combustion engine it previously had reached 400 horsepower. Among the many challenges, the problems the team faced in converting from one propulsion system to another were complications with weight distribution during flight. While the electric motors were lighter than the original engine, the battery pack still weighs the same when it discharges compared to a conventional airplane, where the total weight reduces as the fuel is consumed. To compensate for this, the aircraft was converted into a single-seater to further reduce weight, albeit at the cost of moving the center of gravity slightly forward, because the battery packs occupied a large part of the aircraft, keeping both its weight and volume within an acceptable range, and turned out to be one of the main design challenges. The designers described it as a large flying battery where meticulousness went awry in trying to meticulously arrange each component. Traditional designs of electric vehicle batteries are too heavy for use in aviation, so the ACL team turned to Formula E. These electric racing cars, similar to a Formula 1, proved to be a perfect source for the innovation of creating the lightest possible batteries. A battery pack designed around 18 modules was ultimately chosen. Each module contains 120 cylindrical lithium cells. The cell used was the popular 18650. A unit that is based on nickel, magnesium, and cobalt compounds. Inside each module, they are tightly packed and a liquid cooling system was developed consisting of a cooling plate in contact with the cell that circulates a mixture of water and glycol through them. Each module produces 120 volts with a capacity of 4 kilowatt hours and are capable of fully discharging in just over 3 minutes. When combined into a battery pack, these 18 modules resulted in a 720 volt battery with a capacity of 72 kilowatt hours, which gave a 3-pack propulsion system a capacity of 216 kilowatt hours. Using techniques used by Formula E teams to reduce cell weight, Axel's team had designed a special containment system for the batteries that also served as a structural part of the aircraft. From this, they managed to reduce the weight of this part from 450 kilograms to just over 300 kilograms. The battery pack of this plane has a specific energy of 168 Wh per kilogram, making it the highest energy density battery ever used in an electric aircraft. It is estimated that this battery system is capable of providing a flight range of up to 320 kilometers. However, electric technology is still far from the 500 watt-hours per kilogram needed to compete with traditional jet propulsion for commercial flights. Designing the propulsion unit for the spirit of innovation was also another major hurdle for the team. Not only the electric motor must be compact and powerful, but it also must possess a high degree of reliability and the ability to tolerate failures for use in aviation. There was not a single commercially available electric motor that met these requirements, so the designers opted for a configuration of 3 axial flow electric motors and ASA 750R, coupled by a single shaft that drives a 3-blade propeller spinning at about 2,400 revolutions per minute. Axial flow motors have rotating rotors that are thinner but larger in diameter than conventional radial motors, which rotate along a stator instead of inside it. This larger radius offers 30% more torque density for the same permanent magnet, and IASA technology made them weigh as little as possible. The 750R motor proved to be extremely rigid and easy to integrate with other systems, and using 3 of these motors in tandem, that is one behind the other, not only met power requirements, but also offered redundancy against failures of 1 or even 2 motors, while the entire triple motor system weighed only 111 kilograms. It is capable of generating around 750 kilowatts or 1,000 horsepower, but it is limited to around 210 kilowatts or about 280 horsepower due to thermal restrictions. Unlike vehicles like electric cars, aircraft require larger amounts of continuous energy simply to fly at cruising speed. This creates safety issues as the high voltage consumption, combined with the density of the propulsion system, generates significant amounts of heat. Also, keep in mind that it has a battery failure mode, as they can catch fire and easily trigger a domino effect leading to a disastrous thermal leak. For this, 2 independently managed liquid cooling systems were installed with 4 cooling pumps where they channel the absorbed heat through the battery cooling plates and the engine's internal cooling ducts to a side-mounted radiator. Within each individual cell, voltage and temperature sensors were placed for thermal management and safety, providing the driver with information about the battery status and alerting about possible failure conditions. The containment structure with thermal insulation is designed to be fireproof using a purge mechanism that maintains an inert argon atmosphere inside. The hardware and electronics for managing the nearly 20,000 sensors on board were housed in an avionics bay installed directly behind the battery packs. Before the flight tests of the Spirit of Innovation, a series of extensive ground tests were carried out, and this was done on one of the kits that had been built as a static test aircraft, without wings, known as Ironbeard. By September of 2020, more than 122 hours of ground tests were conducted on the test bench, with a strong emphasis on testing the reliability of the battery system. From here they determined a strategy to extract the maximum possible performance from the battery system. For the flight tests of September 15th, 2020, which was its first flight, Rolls-Royce's chief test pilot, Phil O'Donnell, flew for only 15 minutes and reached a speed of 337 kilometers per hour. Over the next few weeks, about 30 flights were conducted with increasing speeds as the functionality of the propulsion system was validated. It was soon discovered that the cooling systems worked beyond what was expected in ground tests due to the addition of the cooling effect of high-speed air in flight. The batteries were designed to provide high output power for a short period of time. Most of the flights consisted of 7 to 8 minutes at high speed near maximum power, and the team contracted a Spitfire for these flights to follow the plane in its tests, as it was fast enough to do this. Rolls-Royce test pilot Phil O'Donnell described that the aircraft was not very different to fly than those he was used to, but it does have unique characteristics. For example, the engine does not need to be at idle. That is, it will be completely without turning the propellers until power is given when one needs it. Once in the air, they provided thrust in a very linear and responsive way. Unlike any combustion engine, between flights, the battery packs could be individually recharged in an hour, although this was mainly limited by the electrical infrastructure, although in the near future they could be reduced to just 30 minutes. Regarding the behavior of high-capacity batteries in the use of aviation, unlike electric cars, electric aircraft subject their batteries to much more frequent full discharges than road electric vehicles, which drastically affects the battery life. For example, the team had determined that they can only be recharged between 500 to 1500 cycles before they degrade beyond the safe limit for flight. Airports should also be equipped with higher capacity battery charging infrastructure to operate virtually even small electric planes, although partnerships are being explored with various electric propulsion aircraft projects throughout Europe with several of these. The projects even seek transition technologies to power large aircraft, such as hybrid electric systems, advanced gas turbine engines, and sustainable aviation fuels, all with the global goal of bringing aviation into a new era of electric flight. I hope you enjoyed it until a new installment of Aviation World. Thank you.